We're now going to look at a new class of ordinary differential equation problems known as boundary value problems. So what is a boundary value problem? Well, a boundary value problem is an ODE problem in which specified conditions have to be met at boundaries and one or perhaps more adjustable parameters exist whose values are not known. Typically what we're trying to do is we're trying to find the parameter values that ensure that the boundary conditions can be satisfied. So the task is twofold. Determine the values of the adjustable parameters that ensure the boundary conditions are satisfied, and once we've found those, determine the solution at positions other than the boundary values. And a perfect example of this is the equation of motion for a projectile. So let's have a quick look at that to try and explain this a little bit better. So imagine we have a howitzer there that's firing a projectile, and we have a particular target somewhere across here that we're trying to hit. The equation that describes the motion of the projectile is this vector equation. R is actually has components of x, y and z. D squared r dt squared is equal to g minus cd, absolute value of v times v, so there's a drag term and a gravity term. The boundary condition we want to satisfy is that the projectile has 0 altitude when its range is equal to the target range. In other words, when we're across here, we've actually hit the target. The adjustable parameter that we have is the angle at which the projectile is fired. Let's assume here that the muzzle velocity is fixed and can't change. Let's have a look at this schematically then. So let's just arbitrarily choose some parameters. Let's say the target's 13,500 meters away, the muzzle velocity is 800 meters a second, the height of the barrel above the ground is 4 meters, and our drag coefficient CD is equal to 0.4. And what we're going to plot is we're going to plot, as the projectile is travelling, its height as a function of distance from the gun. So let's plot those two things here. Let's see what happens when we choose an angle of 5 degrees. We get the blue curve there. We see that the projectile doesn't go very high, but it goes about 7,000 meters. If we change the angle to 10 degrees, we get to about 10,000 meters. Change the angle to 15 degrees, we probably get to about 12,500. 25 degrees, we're probably around 14,000. 35 degrees, closer to 15,000, etc. So the distance the projectile travels depends on the angle of the barrel. Let's plot distance then as a function of angle. So we're going to call this function d of theta, and we're going to get a plot a little bit like this. So the range, that's d of theta, as a function of the angle, which is theta. So our target is at 13,500 meters. How do we find the angle that's going to give this range? Well, the range is represented by that red straight line there. So clearly where the blue line crosses the red line, the values of theta there are the angles that are going to give the correct range. This kind of issue or problem is the essence of a boundary value problem.